Hi everyone, welcome back. In this video, we'll be talking about spherical lenses. So in our last video, we have talked about spherical mirrors, and in this video, we will be extending the concept just a little bit to the spherical lenses. So for spherical lenses, we will also have the center um, of an imaginary circle and the focal point. But this time, I will be uh, drawing the center as 2f and the focal point as f, because we know that the center is actually 2 times the distance from the lens to the focal point away. And on the other side of the lens, I will also say f and then 2f. And for the first lens we're seeing here, this is a converging lens. And also it's called a convex lens. While for the second one right here, it's called a concave lens, also a diverging lens. And from our experience from our last video, where we talked about spherical mirrors, we all know that for converging lens, all the light rays converges together, and for diverging lens, all the light rays diverge from the lens. So we will see how this has an effect on how light rays behave on uh, the different lenses. So for converging lens, we will expect something when we have all parallel light rays coming into the lens. We can expect all light rays to converge at a specific point, which is the focal point. So if I draw a couple of parallel rays coming into the lens, all of them should converge at the focal point. So that is what the converging lens mean. So the lens will converge all the parallel rays at focal point. And now we will be looking at a couple of how the image of a converging lens will look. So our first example will be something like this. So we will first use a up arrow to represent our object. And then we will start by drawing our first light ray, which will be a parallel ray going through the top of the object. And ideally, it will be converged at the focal point, as we talked about earlier. The second point will be a light ray going right through the center of the this is not very accurate. What I meant was a line going through the center of the lens as well as the top of the object. And the third one is where we go through the top of the object and the focal point of the lens at this side. And then we will have a parallel light ray going out through the light ray. So ideally, we would have all the light ray. This is not drawn to scale, especially the focal point and everything. So ideally, all these light rays should converge at one point, and this would be the top of the object, the image of the object. So we can see that the object is actually enlarged. It is enlarged. It is upside down, so it is inversed, and it is actually a real image because we this is formed at the other side of the lens. So we will see that for converging lens, it is not very super complicated, and a very a simple rule of thumb is that if the object is placed between f and the lens, uh, it will form a virtual, upright, and enlarged image. And this is actually how magnifying glass works. If the object is placed in between the lens and the focal point. And if the object is placed in between the first focal point and the second focal point, between f and 2f, we can see in this example right here, it will form a large, inversed, and real image. And when an object is placed outside of 2f, it will form a smaller, still inversed, and real image. So we can sort of see that all real images are actually inversed. And depending on which side of 2f the object's on, it is either smaller or larger. And depending on which side the object's on relative to f, we can decide whether it's a virtual image or real image. So that is all for converging lens or convex lens. Now we will be looking at concave lens or diverging lens. So before that, I will first be moving this down a little bit to give me a bit of space right here. And then we will start by labeling F and 2F, center of the lens, F and 2F. So for converging lens, if I still draw a couple of, let's say 3 parallel light rays, you can expect other light rays to diverge from each other. So that is the concept of a diverging lens. And now we will see how the image of a diverging lens will be formed. So let's still pretend that we have a object here, and we will start by drawing the first parallel light ray. And this will be diverged from the lens such that it will extend through the focal point at this side. The second light ray that we're going to draw for this one is still a light ray that goes right through the center, because that will never change. It will always be like this, will never refract, so it will just simply go straight through the center of the lens. And the third light ray that we are going to draw here will be one light ray that goes through will be a line that goes something like this. So we will pretend that it goes through the top of the object and this focal point right here. So we will pretend that it actually extended through the focal point at the other side, and it will come out parallel to the axis. And if we extend it back, we will see that this time all the light actually converge at one point, and this will form a smaller, I will mark it in white. So it's actually this image right here, and we can see it is actually a upright. And we know that all upright images are actually virtual, and it's a smaller image. So that would be the characteristic of the image formed by this particular object here by a diverging lens. And probably one of the most important application of a concave lens or a diverging lens in real life would be the glasses we wear if you're nearsighted. So both lenses are actually a diverging lens if you look at it closely. So so that would all for the different mechanism of these two different lenses that are being widely implemented in the world. So converging lens and diverging lens. And we also look at the image forming patterns and mechanism of both lenses as well. So I think that has been helpful. And thank you for watching.